as we already know that this vinyl chloride monomer production involves three different steps. So it's okay to to know some of the advantages and also the limitations of this of this of this method. Yeah. So let's see one by one. So you need to, so before touching the Aspen HYSYS software, you really need to know the in and out of the process. Yeah. So you really need to know what goes inside, what comes out, what could happen during the process. Is maybe you your product may degrade, for example, or you may lose your product by due to combustion in this case, or you may get some other side products. You may end up with a lot of impurities due to some unwanted reaction that may happen during the course of the chemical reaction. Yeah. So these are some other information that you should be aware of. So you don't have to consider all those details while you're going to develop the process flow sheet, but as a chemical engineer you must know what could happen. Yeah. And so so these are the things I want to cover. So I already wrote a few things, so that may give you some idea what I'm talking about. So if you take, for example, this oxychlorination process, this process can produce a lot of chlorinated waste. Yeah. So in fact, purely from environmental viewpoint, producing vinyl chloride manufacture just using those first two steps, which is like a direct chlorination of your ethylene to, to ethylene dichloride followed by pyrolysis, is one of the cleanest process. But on the other hand, still you get hydrochloric acid and you don't want to waste it. Yeah? So if there is a way to recycle back, and if there is a way to achieve near to that stoichiometric efficiency, why not to go for the next process, which is oxychlorination process. Yeah. So we should know some of the we should know how to use the byproduct and the intermediate that may be produced during the process, but at the same time we should also worry about our environment. Yeah. So we should also look for the a clean process, and in fact we should try to minimize the formation of any impurities, or if you want we can call it like undesirable products. So that may pollute our environment. So these are some things that you should be aware of. So typically oxychlorination process, if we they may produce a lot of chlorinated wastes, and so I just listed this, just what are the possible impurities, like trichloroethane, like a chloral compound. So this is something that we don't want to see. It can polymerize, and after that the degradation of the polymerized product is even more, it's not a good idea. Yeah, to have this type of products in the product stream. And also trichloroethylene, and also methylene chloride, chloroform, and also polychlorinated high boiling compounds. So these are some of the products that we may see in the product stream when we go for an oxychlorination process. Yeah, but obviously we can minimize them. It depends on what temperature we are using, and how well we optimize the process in order to convert your reactants into products. So something we can call it like a reaction efficiency. So obviously these are the things that should come to your mind. So obviously we know that, okay, we are going to produce this particular product and we are going to follow these three steps, and so some of the process have some advantage, like and whereas the third one, oxychlorination step, it can bring some impurities into the product stream and so on. Yeah, so these are things that you should keep in your mind when you take a design project. There are few other methods to, or how do you call, like a few other process that you can think about while you are going to manufacture a vinyl chloride monomer. Yeah. So for example, we can just stick to the direct chlorination. Obviously you will end up with a hydrochloric acid, and if you want to use this hydrochloric acid, instead of going for an oxychlorination process, we can go for an decon reaction. Yeah, decon is the name of the guy who developed this process or this synthesis procedure. So 2 moles of hydrochloric acid reacts with half a mole of oxygen to give chlorine. Chlorine, just to remember, this is a gaseous product. We're performing this reaction at a very high temperature plus water molecule. Yeah, so this is one way to recycle your hydrochloric acid into chlorine, and this chlorine obviously we can use it as a reactant in order to produce more vinyl chloride monomer. Yeah, so we can use this chlorine for the direct chlorination reaction. We can use this chlorine for the direct chlorination of ethylene in order to produce ethylene dichloride. Yeah, so this is something to you should keep in mind. So for the moment, for our project, we are going to produce vinyl chloride manufacture using this vinyl chloride monomer using these 3 reactions like direct chlorination followed by pyrolysis, and then we are going to take the hydrochloric acid from the produced from the reaction 1, which is direct chlorination, and then we are going to mix it with what, with ethylene to get. Imagine if we decided to go for a direct chlorination reaction alone, so we can use this chlorine in order to produce more vinyl chloride manufacture using the simple direct chlorination reaction. Yeah, so keep these things in the mind. So whenever we are going to or whenever you are going to deal with a design project, you should go into literature and just look for the information. So how many methods are available in order to produce that or in order to manufacture that product. Yeah, so look at the reaction stoichiometry and check is there any way you can use all those intermediates and byproducts. So this decon reaction allows to convert your hydrochloric acid into chlorine. So this is a chlorine gas. Obviously we can use this chlorine in order to produce more vinyl chloride monomer. Yeah, so we can recycle this stream back into the process. Obviously we have to control the temperature of the product stream, so and then we can recycle back into the main process. So in order to something like you take this chlorine plus ethylene, and then you get ethylene dichloride. Yeah, so keep these things in your mind. And then so why are we talking about all these processes is like so before touching the software, obviously we need, as I said, we need the full reaction stoichiometry, and then we also need to think about what are the other ways to deal with this design project. Yeah, for example, I can remove the third step, which is oxychlorination of ethylene to ethylene dichloride, and then I can replace it with the decon reaction. Yeah, so it will also make the process more efficient. In fact, if you search into the literature, you will see many industries use just the direct chlorination, and then they use the decon reaction in order to recover the hydrochloric acid. And there are so many industries they use all the 3 reactions that we already talked about. They use direct chlorination, pyrolysis, and then they also recover the hydrochloric acid using the oxychlorination step. So keep these things in the mind. And if you're really curious about the different methods to recover hydrochloric acid, there is a very nice review paper. You can read this article. It's published in, please see the article. I think I forgot to add the article title. Maybe I can send you by email. It was published in Chemical Engineering Science, I think. So there they listed the different methods available to, or different methods, and also the reaction that allows you to recover hydrochloric acid. Let me quickly check my notes. I really don't. I'm not sure what's the author. Who are the authors? I remember it's published in Chemical Engineering Science. It's a very old paper. Maybe I will send the article by email, yeah. So whenever you think about your design project, just look for all the options in the literature, like how to manufacture a product more efficiently, and also is there any way to use the byproducts produced during the reaction, and check for probably you can produce the the same product using more than one technique, and you can also recover the byproduct using more than one technique, yeah. So check for these details in the literature all, and it's up to you to to select which process to use, or you should first you should be convinced for, okay, I'm going to go with these three different processes for so and so reasons. In this case, we like the direct chlorination process. It's very clean, and but it produces hydrochloric acid, and we are going to add oxychlorination process because it allows you to recover that hydrochloric acid efficiently, and it also keep the stoichiometry completely closed, yeah. So which mean our process is fully balanced. So at the end of the day, the we are going to get only vinyl chloride monomer as the product, so there will be no byproducts, which is something that we need. So that's a justification that we've selected these three different process, or if you or if you can just talk like a chemist, like we prefer to select these three chemical reactions, yeah. So that allows you to produce our product. So at the moment, what we are doing is we're just gathering the information, and we are trying to make a plan that allows you to to draw the process flow sheet, and then finally we will perform the process simulation using Aspen HYSYS. So we are just collecting the information using the it's not even, so whatever the things that we talked, it's not even chemical engineering, they are pure chemistry. So we are just only looking at the reaction chemistry. We talked about the reaction stoichiometry, we talked about the heat of the reaction a bit, and then what we talked about, we keep a note on the byproducts produced during the chemical reaction, and then finally we try to make use of those byproduct in order to increase the productivity, yeah. So these are the things that we collected so far, and we need few more information before we go to the Aspen HYSYS. And always remember that whatever the products that we are going to produce, they are not going to be pure, yeah. It will be impure. The product stream may contains a mixture of product, and also some of your reactants which are not yet converted into product. So which mean we also need to separate your products from other materials, yeah. So which mean we also need some unit operation that allows you to produce or purify your product, yeah. So keep these things in the mind. So we are just collecting the information, yeah. And also remember, Aspen HYSYS is not a magician, like once you draw the process flow sheet, and it's not going to solve the problem by itself. We need to give the right level of not right level, the correct information as well, yeah? If not, we cannot Aspen HYSYS cannot perform the calculations. So keep these things in the mind. So that's why we are gathering all this information. So, and then I wrote few things already here. So as I said, in this project, or at least for our lectures, we will select the combination of direct chlorination of ethylene and oxychlorination of ethylene. As I said, these processes complement each other and ensuring a tight closure of the material balance, yeah. So that you are, so remember this tight closure of material balance. Whenever you see this buzzword, which mean the final stream will contain only vinyl chloride monomer, and no byproducts, yeah, so or no intermediate products. So that's the whole idea. So since we already covered the reaction stoichiometry, we will go to the process in a bit more detailed way. So that's, I wrote something already here. So let's begin with this step 1, which is direct chlorination of ethylene to ethylene dichloride. And normally we can perform this reaction. So now we are going, we are introducing this chemical engineering aspect, yeah. So at what temperature we are going to perform this reaction? So we can perform this either at a low temperature or at high temperature. So this is some, so it is your job to to go to the literature, or you can even check the different patterns, like so at what temperature they perform this type of reaction and which one is efficient, and you have to convince yourself, like why I select, so why I'm going to perform this particular reaction at that particular temperature. You should be you should convince me, and you should also convince yourself, yeah. So let's see how this process works, yeah. So you can produce this at low temperature, at 50 to 70 degrees centigrade and 0 to 2 atmosphere. So this temperature and pressure is, we can understand what it is, but you should also know about the fluid properties a bit. So at 50 to 70 degrees centigrade and at pressures of, and at a pressure of 0 to 2 atmosphere, we are below the boiling point of ethylene dichloride, so which means your product will be a liquid. You can perform the same direct chlorination reaction using at high temperature, say 90 to 150 degrees centigrade at 1.5 to 5 atmosphere. This is your pressure. And both of these reaction normally we perform using a catalyst, will be FeCl3 catalyst. But in this case, your final product will be above the boiling point of ethylene dichloride, which means you will get your product in a gas form, yeah. So it will, your product will be in gaseous state. So now you have to think which is more advantageous for us, product in a liquid format or in a gas format. So both of these have some advantage, and both of it have some limitations as well. So we will try to see what are the advantages and the limitations. So low temperature conversions is, we can perform easily in a gas liquid contactor, and normally this process is widely used in industry. And the main advantage of this low temperature conversion, or sorry, low temperature chlorination, is the efficiency, and it has a very high selectivity towards ethylene dichloride. So which means 99% of your reactants will be converted into ethylene dichloride rather than into other intermediate products. So which means the efficiency is extremely good, and that's why industries like this technique. So that's why they do direct chlorination at low temperature and also at slightly lower pressure, 0 to 2 atmosphere, and obviously both are below the boiling point, which means you are going to get a liquid product, yeah. So, and however this process requires catalyst removal from the product stream, and also requires heat removal, yeah. So normally it may look something like this. I can draw the diagram. So your reactor may look like this. So you get two of your gas streams. So you start with the two reactants, which is in, I changed the pen. So you have two reactants. So one is your ethylene, another is your chlorine. So both are in gaseous state, and then we are performing this at a temperature of say 50 to 70 degrees centigrade, and then a pressure of 0 to 2 atmospheres. So you will get a liquid product. You will also see some vent, some gases to come out. And since as I said, this is a highly exothermic reaction, minus 218 kilojoules per mole. So we have to to remove the heat using some internal coil, yeah, in order to maintain the temperature of 50 to 70 degrees centigrade. So this is something that you should remember when, if we decide to go for a low temperature direct chlorination at low temperature, then you should think about how to remove the heat. So we need an external temperature control. So follow the highlighter now. We need an external temperature control in order for or maybe you can even put a simple jacket in order to remove the heat produced during the reaction. So this is one disadvantage, not disadvantage, maybe the practical limitation of low temperature chlorination. But on the other hand, it's like the efficiency is very high. The selectivity towards ethylene dichloride is extremely high, almost near to 100%, which means all of your reactants will be converted into the desired product. Or we can go for a high temperature chlorination. So high temperature chlorination, the selectivity is very low when you compare with low temperature chlorination, but it offers a better heat recovery. So we will see this soon. What do I mean by this? So as I said, the high temperature chlorination is like we are going to perform at what temperature? So 90 to 150 degrees centigrade, and then 1.5 to 5 atmosphere. So this is above the boiling point, above the boiling point of ethylene dichloride. So which means you will get some gaseous, oh my god, let me change the pen, sorry. So just wrote here 90 to 150 degrees centigrade, 1.5 to 5 atmospheres. So this is above the boiling point of ethylene dichloride. So which means your fluid or your product stream will be in a gaseous state. And also the heat of reaction is also 7 times greater than the heat of vaporization. So which means your product stream will definitely be in a gaseous state. So this is something that you should know. Yeah, these are simple basics. Yeah? If you boil the solution above the boiling point, obviously you will end up in producing gas. Yeah, so this is these are two basics. I think I don't have to even explain. So let's say this, let's see how to perform this high temperature chlorination. So normally in industries, so let's say this is your reactor. You have your chlorine, you have your C2H4, and obviously, so we are performing this at a high temperature, so 90 to 150 degrees centigrade, and then 1.5 to 5 atmosphere. And remember, it will produce ethylene dichloride that will be in a gaseous state. So what we can do is like so since your product is in gaseous state, so since your product is in gaseous state, the heated stream, we can use it for the purification of the stream. Yeah, like say like if this stream contains say ethylene dichloride plus some other compound, say HCl for example, or it can we may even have some products like trichloroethylene. So we can take the heated stream which is already at a higher temperature, and then we can connect it to something like a distillation column with a reboiler. Yeah, so normally distillation column will have a something like here. Yeah, we will have a reboiler in the bottom, so that allows you to heat your fluid which is inside. But since your stream is already at higher temperature, so we don't need this reboiler in this setup. Yeah, so you just feed it into the column. Okay, we don't okay, let's say take the stream out, then we can feed in the column like this. So this heated stream will automatically act like a natural reboiler. Yeah, and then take the light products out, which will be pure, which will be now typically ethylene dichloride, and then we can remove the heavier products in the bottom, and then some intermediate products, say trichloroethylene. So instead of using a separate reboiler, since your stream is coming from relatively, since your stream is maintained at a relatively higher temperature, say 150 degree centigrade, so this itself act like a reboiler. So all you need is to make a like a special device without a reboiler. So you just pump the stream inside, and then you take your light products, in this case ethylene dichloride, at the top, and then you take the remove the heavier product from the bottom. Yeah? So so the whole idea is like we can connect this stream to a distillation column, and this heated stream in itself will act like the reboiler of the distillation column. Yeah, so we can design such an equipment, why not? Yeah, so but for our project, or for our design calculation, we are going to stick to the low temperature chlorination, because and the justification for selecting low temperature chlorination is its very high selectivity towards ethylene dichloride. Yeah, so it's better we convert all of our reactants into products. Obviously we have to think about other type of purification, because if you go for low temperature chlorination, as I said, so your final your product will be a liquid, and we don't have to install this distillation unit at the moment. So we have to think about other type of separation techniques in order to purify that liquid, yeah? In order to get near to 100% pure, or say 99.5 or more than 99% pure ethylene dichloride. So we will come back to this later, but for the moment, so we already decided we are going to go for a low temperature chlorination, and we know the temperature and the pressure condition. So we gathered some information that we need for the design project. Yeah, so let's see. And then since we fixed the mind already, we are going to go for low temperature chlorination. Let's write the process conditions. So let's say we are going to perform this chlorination reaction, say at 60 degrees centigrade, temperature is 60 degrees centigrade, pressure of 1.5 atmosphere, and now we need to think about the reaction kinetics, how fast your reactants are converted into products. So reaction kinetics, so we need to define some rate law that allows you to calculate the rate of the reaction. Yeah, so obviously this is some information that you need to get from the literature. I already checked in the literature, so it's from HYSYS. It's published in Chemical Engineering Science, volume 56, year 2001, page number 513 to 522. So there they reported the reaction kinetics, or they defined a rate law for the conversion of your reactants ethylene to ethylene dichloride, and it follows the simple rate law. R is equal to, just put R is equal to K1 concentration of your ethylene and then concentration of your Cl2, and the units is in kilomoles per meter cube per second. And they found that the reaction is a first order with respect to ethylene. So reaction is first order with respect to ethylene. So this is some other information that we need when we are going to use Aspen HYSYS. Yeah. So they gave some number for kinetic this kinetic constant K is equal to 11493 exponential of minus 17929.81 divided by RT divided by RT, yeah. And the units, always pay attention to the units, meter cube, kilomoles per second, and this is in joules. 17929.81, this is in joules. So that's your activation energy, and this is your pre-exponential factor. So the kinetic constant follows the Arrhenius expression. Yeah. So these are some information that we need. So this is for the direct chlorination part. Direct chlorination of ethylene to ethylene dichloride. And then now let's go to the oxychlorination part. So oxychlorination, we are dealing with the reaction kinetics, so don't forget. So oxychlorination of ethylene to ethylene dichloride. So normally we conduct this reaction in a fixed bed, or probably sometimes in a fluidized bed, and normally this reaction is carried out at a very high temperature, so around 230 degrees centigrade to 300 degrees centigrade, say using a fixed bed reactor. If they use a fixed bed reactor, they perform this reaction at a temperature that within this range 230 to 300 degrees centigrade, and normally the pressure will be in the range of 1.5 to I think around 4 atmospheres. And then if they perform in a fluidized bed reactor, so if we perform the same oxychlorination reaction in the fluidized bed reactor, they perform this reaction similar at roughly around 220 degrees centigrade to 235 degrees centigrade, and in the pressure range will be somewhere around 1.5 to 5 atmosphere. So these are some information that we need. Yeah? So you have to fix your mind now. So which reactor are we going to use? Is it a fixed bed reactor or a fluidized bed reactor? So if it's a fixed bed reactor, what will be the process condition, at what temperature I perform this reaction, and what will be the pressure inside the reactor. So this is something we need to remember, and we also need to find some reason which one to use. So for example, if you use a fluidized bed, it offers a better heat transfer, and also if you use a packed bed, it may create some active temperature spots. Yeah? It's like a occurrence of hot spot inside the reactor, and this can be avoided in a fluidized bed reactor. So this is some advantage of using fluidized bed reactor, but in this exercise I'm going to stick to the fixed bed reactor, and we are going to design a fixed bed reactor, something like a plug flow reactor, which is very easy to implement in Aspen HYSYS. And obviously we are going to not we are going to use so we are going to model this plug flow reactor as a catalytic reactor, so it will contain some catalyst. And I forgot to mention these two reactions, they perform in presence of catalyst, and normally they use copper 2 chloride. So that's the catalyst they use, copper 2 chloride. And if we go to the normally copper 2 chloride, impregnated on onto alumina particles, and typically the catalyst loading will be roughly 4 to 5 weight percentage. Yeah? So obviously you can check the literature, someone might might have used completely a different type of catalyst. So I recommend you to read this paper, Chemical Engineering Science. So it's published in volume 23, year 1999, 479 to 495. That's the page number. So there you can find this reaction stoichiometry, and also the heat of reaction, and few other information. And also so I think this is good so far. So we need a reaction kinetics, so how fast the reaction proceeds. So so one of the so you can check in the literature by yourself. Anyway, I did it for you. So in this case, so the rate of reaction, so this at the moment we are talking about oxychlorination. Yeah, so the rate of the reaction, this is a catalytic reaction follows a Langmuir-Hinshelwood kinetics. So the direct chlorination follows a simple first order kinetics, and this oxychlorination will follow the Langmuir-Hinshelwood kinetics. And I got this information from the paper. Okay, I'm not going to write the title of the paper, you can check it. It's published in Industrial Engineering and Chemistry Research. So we simply call it as IECR. You can check in this volume 33 and then 259 to 264, and author is I think Wachi and Askai. Just to check the manuscript. So they already calculated the reaction kinetics for us. So they performed in the lab scale reactor, and they found that the reaction follows the Langmuir-Hinshelwood kinetics given by R is equal to Kr, Ka, then C concentration of ethylene, and then concentration of chlorine divided by 1 plus Ka concentration of ethylene. So Kr is your kinetic constant, and it follows and it changes with respect to temperature, and which follows an Arrhenius type expression. So Kr is equal to 269 exponential minus 37.8 by RT. So in this case, this is expressed in kilojoules. So your activation energy is in kilojoules. Always, if it's okay, anybody can go to literature if you know how to use the literature, and you can get this type of information, but you must pay attention to the units involved. Yeah? So pay attention to the units. So K 37.8 kilojoules per mole, and then So obviously if you want, you can convert it into joules. For example, 269 say minus 37800 by RT. So that will make this activation energies into joules. And they also reported the Ka. Ka is something related to absorption constant. So absorption of your reactants onto the catalyst. So this values I took from literature, 0.63 meter cube per mole. So this will be equal to 630 meter cube per kilomole. So we are converting wherever we see the units in terms of mole, we are going to convert it into kilomole for consistency and also for our own convenience. Yeah, and so and if you even for your final year design project, I know at the moment we are dealing with the completely other module CG5031, but for the next year when you are going to deal with the design projects, you are going to use Aspen HYSYS for many good reasons. So during that time, these are the information that you should look into the literature. So okay, say like I'm going to give you like a manufacturing of citric acid, for example, and if it's an enzymatic reaction, if the process involves an enzymatic reactions, say for example, you need to go to the literature, check in the literature, look for the reaction kinetics, look for the kinetic constant, and check whether how it changes with respect to temperature, what's the activation energy, and so on. So these are the equations, these are the information that you should look before you think about designing full designing any chemical engineering plant. Yeah, so just keep these things in the mind. So whenever I say like I need some information from literature, these are the information that I need, like the basic reaction stoichiometry, the heat of reaction, and also the conditions where at which, or how do you call, like the process conditions, like what temperature favors that particular reaction, and what type of catalyst I need, or whether do I even need a catalyst to perform that reaction, and whether I can perform the same reaction at different temperature, and if I can perform at different temperature, what are the, so which one I have to choose. Yeah, like and why. So okay, like if I use for a high temperature chlorination, I get a gaseous product. If I go for a low temperature chlorination, I get a liquid product. And if I use a gaseous product, then I can connect it to a simple distillation column that allows you to 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 purify the product um, without attaching a reboiler to the column. Yeah, so these are the things that you should think when you are going to design a project. And the whole idea of this module CG5031 and the purpose of learning Aspen HYSYS is to train you, so that train you to use Aspen HYSYS, but also get you ready for the final year design project. So that's why I'm going a bit slow. That's why I'm even explaining you like what are the information that we need. Yeah, like for me it's very easy to open the Aspen HYSYS software and directly start showing, oh, these are the components, these are the things that we add, and these are the stream that goes in, these are the product stream that comes out. But it will be like a completely blind process. You will have no clue why we did that. And that's why I'm going a bit slow. And at the moment we are learning, we are studying how to studying about the vinyl chloride monomer manufacturing process. But we are also studying or learning what are the information that we should gather from the literature. Whenever I say literature, it refers to research articles, textbooks. Also, you can also get a lot of information from patents. There are a lot of chemical engineering encyclopedia. So you have to search all these. Mm, uh, uh, you have to search in in in, in in different places. Yeah, like so it's okay. At the moment I used two different research articles, but obviously if you go to, so at least at the moment you know, like at least for this particular process, you know, okay, these are the information which I am collecting at the moment, and I'm going to use it to develop the full flow sheet. So let's come back to this topic. So Ka is the adsorption constant, 630 meter cubes per kilomole. And if we go to this, the work of, what's the author name? Wachi and Askai. I don't know how to spell them. So if in the rate equation, let's put R, capital R. Here, whatever you see here, concentration of Cl2, so this refers to the concentration of Cl2 in the catalyst, and they already calculated for us, and this is equal to 0.993. So this is not the Cl2 that enters the, sorry, Cl2 is the concentration of the Cl2 in the catalyst, copper 2 chloride. So they already calculated the concentration of Cl2 in molar units. Yes, yeah, 0.993 moles per meter cube. Obviously I'm going to convert it into kilomoles. So remember, this is for oxychlorination reaction. Yeah, so at the moment we are dealing with the oxychlorination reaction, and your reactants are ethylene, and then hydrochloric acid, and then some oxygen. So obviously there is no Cl2 in your reactant side. So obviously the Cl2, sorry, let's write ethylene, C of Cl2 divided by Ka, 1 plus Ka, concentration of ethylene. So this is the concentration of chlorine in the in your catalyst. Yeah. So now we have some parameters. We know the value of Cl2, which is a constant, and then we know the rate constant, and we know the adsorption constant. So we can use all these values to simplify this expression. Yeah. So let's do that. 269 multiplied by 630 multiplied by 993 multiplied by C of ethylene, and then multiplied by this whole exponential term, minus 37,800 by RT divided by 1 plus 630 concentration of ethylene. So we can simplify this expression. I already calculated it. So R is equal to 168,284 concentration of ethylene exponential of minus 37,800 divided by RT. So remember, this is in joules, so don't forget the units, divided by 1 plus 630 concentration of ethylene. So why we are doing these calculations is so we really need to require some serious amount of information before touching the Aspen HYSYS. Yeah, so we, once we open the software, we need like how fast we need the reaction stoichiometry, the process condition, and we also need to know how fast the reaction proceeds and so on. Yeah, so in order to get that information, we need to know the rate of the reaction. So, and we need to get this information from the literature, and sometimes you may not you have to do a bit of calculation. So in this case, we went to the literature, we collected the rate kinetic we sorry we know what type of rate laws that can dictate the whole process. For example, direct chlorination follows a simple first order kinetics, and then for oxychlorination, which is which is a catalytic reaction. It follows the Langmuir-Hinshelwood kinetics, yeah, and then we need to get those values, the rate constant, and then we have to simplify the equation as simple as possible. So and these are the things that you have to do before you think about designing or developing a process flow sheet and also performing any the process simulations. It's not only about Aspen HYSYS. If you use any other similar software which is similar to Aspen HYSYS, still you need this type of information. Yeah, so keep these things in the mind. So in case in fact in the during your final year design project, this is what you are going to do exactly, yeah? So if somebody asks you to design a major unit operation, say a catalytic reactor, then you have to go to the literature, look what type of rate law, the what type of rate expression that you need, and probably if you're going to design a heterogeneous catalytic reactor, probably I think Langmuir-Hinshelwood expression is the most widely used expression, and then you are going to do exactly the same type of calculations. Yeah, so I think we have a rate law for the oxychlorination reaction, and then let's say like we are going to perform this reaction at 225 degrees centigrade, say the pressure at a pressure of 4 atmosphere. So just a reminder, both are above the boiling point of ethylene. Oh no, yeah, we can check this one. This is something that I want to show you while I'm going to use the Aspen HYSYS. You will get some stream. From there we can check the composition plus the state of the fluid, whether it's in a gaseous state or in liquid state. So I want to show you this while when we are using Aspen HYSYS. But for the moment, keep these things in the mind. 225 degrees centigrade, we are performing the oxychlorination reaction at 225 degrees centigrade and at a pressure of 4 atmospheres. Yeah? So now we know a lot of details like about this direct chlorination, oxychlorination, and so on. So and then we can make a simple flow sheet for the moment. Yeah, so let's see, like we have ethylene, that's our reactant, and then say like we need ethylene is the reactant in both your direct chlorination and also in oxychlorination. So we can take one stream and then we can split into two, and let's perform this direct chlorination reaction in a simple CSTR. So we will add catalyst inside, and then we will perform this oxychlorination reaction in a plug flow reactor. So let's assume this is a catalytic reaction, and obviously for direct chlorination we need to supply Cl2, and for plug flow reactor we need to give hydrochloric acid. Normally this hydrochloric acid will be the product from the CSTR. Yeah? So CSTR is going to produce hydrochloric acid plus your main product, which is ethylene dichloride. So but for the moment, let's say we are adding HCl, like a separate stream, and this is your plug flow reactor, and let's maintain the temperature. For CSTR we are performing at what, say 60 degrees centigrade. This is a low temperature chlorination, and plug flow reactor, here we are maintaining a temperature of just now I said 225 degrees centigrade. Pressure we are going to maintain 4 atmosphere. Here the pressure will be, pressure in CSTR will be, let's say 1.5 atmospheres. Yeah, so these are the things that you should remember. And obviously let's say we take the product, and we take the product from both of this, and then we mix them using a mixture. So this will be your ethylene dichloride plus hydrochloric acid. Yeah? So it's hydrochloric acid that comes from the direct chlorination step. So obviously we can purify them. We can purify them. So why do we mix them? So why do we mix them? There is a good reason for that. So instead of adding a separate purification step to one purification step here and another purification step next to the CSTR unit, we can combine the stream and then we can connect, we can mix them, and then you take the final product stream and then you can easily purify them. Yeah? So we will come back to this later. At the moment we are just manufacturing ethylene dichloride is from via direct chlorination and also via oxychlorination. Yeah? So keep these things in the mind. And then we already know how fast the reaction proceeds based on the rate laws. So for direct chlorination we are going to use first order kinetics. For the oxychlorination we are going to use Langmuir Hinshelwood kinetics. Yeah, so these are the things that you should remember. And then so before touching the Aspen HYSYS software, we should need this information. And now we draw a simple process flow sheet, and then we also know the reaction stoichiometry. I will write one more time here. So C2H4 plus Cl2 gives C2H4 Cl2. This is your ethylene dichloride, and then for this is for direct chlorination, and then for oxychlorination is C2H4 plus 2HCl plus half mole of oxygen, giving rise to C2H4 Cl2 plus H2O. Yeah. So why do we need this? Why are you looking at the stoichiometry now? So this is like 1 mole of ethylene, 1 mole of chlorine, 1 mole of ethylene dichloride. Yep. And in the oxychlorination reaction, 1 mole of ethylene, 2 moles of hydrochloric acid, half a mole of oxygen, and then give rise to 1 mole of ethylene dichloride plus water. Yeah. So what we are going to do this, we are going to stick to this stoichiometry. So let's do that. Let's say like for example, so let's draw the flow sheet again. We have a CSTR, and then we have ethylene, so let's say 700 kilomoles per hour. So let's split it exactly into half. That will be 350 kilomole per hour. Another 350 kilomole per hour will go into the plug flow reactor. And then you see here if you come back to the stoichiometry direct chlorination, 1 mole of ethylene reacts with 1 mole of chlorine, giving rise to 1 mole of ethylene dichloride. So we need at least 1 mole of chlorine in order to convert this 1 mole of your ethylene to ethylene dichloride. So we add, so we have 350 kilomoles per hour. So we can add exactly the same amount of chlorine, which should convert this amount of this should, let me write it instead of talking. So this is your chlorine, so which means like we maintain that ratio, 1 mole of your ethylene and 1 mole of your chlorine. Yeah, and that should give your product ethylene dichloride, 1 mole of ethylene dichloride. And normally in the industries, in order to ensure like 100% efficiency, we will add chlorine in excess, say like multiplied by 1.04. So we will add chlorine slightly in excess to that of the stoichiometric amount in order to ensure complete conversion. Yeah, so something like a near to 100% conversion. So now you know some information like 350 kilomoles per hour and then 350 kilomoles per hour of your chlorine. So you will get something around 350 kilomoles per hour of ethylene dichloride. This is an approximate number, yeah. So this is an ideal case. So this information we get from the reaction stoichiometry. So that's why I said before touching Aspen HYSYS, you need to look at the reaction stoichiometry and then obviously the reaction kinetics and other information. Yeah, so it gives the very first information that you need to enter in Aspen HYSYS. So 350 kilomoles per hour. So 350 kilomole. 350 kilomoles per hour. So you can convert this into, so you just multiply it by 350 multiplied by 24, that will be kilomole per day, and then this, just multiply this by 350 multiplied by 24 multiplied by 310 kilomole per year. So this is something like, this is the amount of ethylene dichloride, something that we will produce per year, assuming we are going to operate the reaction for 310 days, and the remaining days we will spend it for cleaning and maintenance. Yeah? So anyway, we will come back to this later. So what we are going to do is like, we will stick to some basis. For the moment, we assume we begin with 350 kilomole per hour of ethylene. So let's call this is our basis, and then from there, and we know the reaction stoichiometry, which means if we know 350 kilomole per hour of ethylene, then we know how much amount of chlorine we need to add, which will be 350 kilomoles per hour multiplied by some, we will add this in excess, so 1.04. so this way ethylene will become your limiting reactant. And then when we are, once we finished developing the full process flow sheet, I will tell you how to adjust the process parameter. Say like if our goal is to produce say like 1 million ton of vinyl chloride monomer per year. So that's our annual production rate. So then how much, what should be the flow rate of your ethylene and your other streams? Yeah, so you will learn this later, but for the moment we select a basis of 350 kilomole per hour, and then from the reaction stoichiometry we know how much chlorine we need to add. So these are the things you need to think when you are going to design a plant. Yeah, so even for the next year, for the final year design project, this is how your mind should work. Yeah, so if, like say like manufacturing of something, then you have to go to the literature, and then you have to select some proper basis, and then you have to check into the reaction stoichiometry. From there you will get some idea how much what's the flow rate of your reactants that should enter the whole process. Yeah, like I think this is good so far. 350 kilomoles per hour, and the same rule apply for the plug flow reactor. If you come back here to the previous page, so 350 kilomoles per hour of ethylene enters the catalytic reactor. So if you go back to the reaction stoichiometry here for oxychlorination, you have 2 moles of hydrochloric acid. Yeah, so how much, what should be the flow rate of hydrochloric acid here? So it will be roughly 2 multiplied by 350 kilomoles per hour, and then you can give this slightly in excess, say like say 1.08 for example, slightly excess to that of the stoichiometric amount. So that should be 2 multiplied by 350 multiplied by 1.08. that should be the flow rate of your hydrochloric acid in order to maintain the stoichiometric ratio. Yeah? So, and in this case again your ethylene will become the limiting reactant, and then obviously you are going to get ethylene dichloride. So we will mix both in the mixing unit, and then we will take the product out, and then and then a few other information that you should know. So what should be the volume of the reactor? So this is something we have to calculate, and then so that volume of the reactor should handle the flow rate, which 50 kilomoles per hour. Yeah. And then another thing that we should worry about is the reaction time. So, or the, if you want, we can call it as a. So for this we have to go to the literature. For in the same manuscript by what was this guy's name? I forgot them. Wachi and Askai. They found that when we need at least 2.5814 hours in order to ensure complete conversion. Yeah. So in CSTR, the TR value should be equal to 2.5814 hours. So we need to fix this. So I will tell you in Aspen HYSYS how to do that. And then in plug flow reactor, remember in plug flow reactor we are the retention time should be equal to 0.09 hours, and then the length to diameter ratio should be equal to 1.5. So we get this information from the literature. So this time ensures near to 100% conversion in CSTR, and TR of 0.09 hour ensures near to 100% conversion in a plug flow reactor. So this is a catalytic reactor. Again here we also adding some catalyst inside. So both copper Cl2 catalyst. So I hope I know this is slightly boring, but it's okay to go a bit slow, you know. If not, you will not understand anything when we are going to deal with Aspen HYSYS. It will, you will, if you don't know all this information, if how do you say, like if you don't know how the process works, how about the reaction stoichiometry, about the reaction kinetics involved, about the how do you call the component flow rate, for like how much ethylene goes inside, how much um, chlorine goes inside, and what could be the the flow rate of the product stream. Everything you can calculate from the reaction stoichiometry, and you need this information before you touch the Aspen HYSYS. If obviously you can go to Aspen HYSYS, you can develop a process flow sheet without knowing this information, just following a simple tutorial book, but at the end of the day you will learn nothing. Yeah? So that's why I'm going a bit slow. So take these things clearly in your mind, and then take a pen and paper, take a note of all the things that we learned so far. Write the stoichiometry, write the heat of reaction, write the rate of the reaction, and then write the kinetic constants involved, and then draw this simple flow sheet which we did at the moment, and then also try to take a note of the temperature, take a note of the pressure, and then take a remember the key factors like low temperature chlorination. The product stream is going to be a liquid, and then the plug flow reactor you're going to get some product stream, and we are going to mix both of them, and then just to remember the 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 the, the retention time, like that ensures a complete conversion of your reactants to product, and obviously we get that information from the literature. And then if you are really curious, also go download this article and check where this information, so like where you can find this information, yeah, like and then highlight those particular sections, so that way you will also know how to use the literature, how to get the information from the literature, yeah, while you are developing your full process flow sheet. So I think we did so far good. So what we did at the moment is like we converted our reactants into ethylene dichloride, but our project is something like we need to convert still we need to convert this ethylene dichloride into vinyl chloride monomer, yeah. So keep those things in the mind. And then a few more things that you should take a note in your pen and in your paper is we are going to add chlorine slightly in excess to that of the stoichiometric amount to the during the direct chlorination. And then for in the oxychlorination reactor, we are going to add hydrochloric acid slightly in excess to that of the stoichiometric amount in order to ensure complete conversion, yeah. So hope I explained moderately okay, I think. So I think so far we did well. So let's stick to this flow sheet for the moment. So ethylene goes inside, chlorine goes inside, HCl goes inside, and then we get ethylene dichloride. Okay, and then now we need to convert ethylene dichloride into vinyl chloride monomer, but before that we need to purify this ethylene dichloride. So normally this ethylene dichloride that we get will be impure. This product stream will contain ethylene dichloride plus HCl plus air products. Sometimes we can even encounter trichloroethane. So trichloroethane is something like you say you have this ethylene dichloride, it can mix with chlorine again, and then it will give this trichloroethane, which is undesirable product, and then plus HCl. So we need to remove both this trichloroethane and HCl. So but in this lecture we are not going to consider this reaction, but still we are going to, in the product we will get all these impurities like hydrochloric acid, some air products, and then ethylene dichloride. So what we are going to do is we are going to separate ethylene dichloride from HCl plus air products, yeah. So we need to get near to say like 99.5% pure ethylene dichloride. And why do we need this? So why can't we just directly pyrolyze your final product that you get from here? Obviously you can take this ethylene dichloride and then go to pyrolysis and then get vinyl chloride monomer, yeah. But instead of doing that, why are we purifying the ethylene dichloride? We need to purify ethylene dichloride in order to avoid coking. That's one reason in the pyrolysis chamber, and also fouling of the pyrolysis reactor. So these are the two main reasons. So even when you are going to do the design project next year, you are going to get you are going to perform a lot of purification steps, and you must know the reason, like why I need to purify an intermediate product, yeah. So there are some good reasons. So in this case we need to avoid fouling of the pyrolysis reactor and also to avoid coking, you know. So these are the things that you should remember, yeah. like cooking in the sense, like imagine if you have a air product and then you have some hydrocarbon like C2H3Cl. Obviously you can, your carbon atom will take one, your oxygen will knock one carbon atom, and then it will go into CO2 or maybe C or something else, yeah, like so. And we don't want this to happen. We don't want to lose the product by this way. So that's why it's better to remove all the undesirable products, and we need just pure ethylene dichloride. So, and also like for example, if you have water H2O, which is one of the product from oxychlorination, it will form azeotrope with ethylene dichloride. So which means we cannot and also with any other organic compounds it will form azeotrope, which means we cannot remove using simple procedures like a distillation, yeah. So thus industries, what they use, so they will use obviously some wash tower first. So you take wash tower to clean, to remove the catalyst from the product stream. So let's go very slow, and then they will use a reboiled absorption followed by a condenser and a decanter. So what do you mean by like so reboiled absorber is something like say it will look something like this. I hope you all know all the basics of if I say reboiled absorber, I hope you all know what's that. So you heat, so you put your product stream, which is ethylene dichloride. So this stream comes from CSTR plus PFR. So you heat them, you heat, and then normally they heat it at a very low temperature, 15 degree centigrade. I'm not sure what's the temperature is about. Yes, they will maintain at a very low temperature so that your water will remain in the bottom, and then your other products will evaporate here, yeah. Your like hydrochloric acid, for example, and then your oxygen will other air products will evaporate. So your light materials will come out, and then here you will get the heavier product. Normally we heat using a steam, and then this will be your condensate, and then whatever the product that comes out here, we will separate them using a, we will add a condenser. And then so this is something what they do it in the industry. So and then they will send it to a decanter. So I will let's draw the decanter down here. So decanter will look something like this. Let me change the color. So this pink one, this will be say like wait a second. So this pink color, this will be say the heavier product, say like water, and then the top product will be, the lighter one will be the hydrocarbons. hydrocarbons. So once you condense, you will get hydrocarbons plus water, and then you pass this stream to the decanter, where you can separate automatically your heavier products from the lighter product. It will have a small weir like this, and your heavier product will overflow, and then we can remove the heavy product from here. So this is something this is what industries exactly do to remove the hydrocarbons from the ethylene dichloride. And so that's the technique they use, that's a strategy they use. So following the same strategy, we are going to purify the ethylene dichloride stream. So but we will use it in a slightly different way. So we have the CSTR tank here, we have the PFR tank here. So whatever the product stream that comes out, we will pass it to a flash separator. So that separates the light gases, in this case HCl plus if there is trichlor ethane or something, it will come out here. Yeah, for the moment it will remove HCl plus any other light components, and then from the heavy component, so this will be ethylene dichloride. Yes, this will be in a liquid form plus water. Yeah, so this should this should give roughly around 60% pure ethylene dichloride. We will check that later using Aspen HYSYS. And then whatever that comes out of from here, we will take this compound, this product, the 60% pure ethylene dichloride, and then we are going to combine, or I'm going to use a liquid extractor. We take the stream, and then we are going to use water as a water as an extraction water as a solvent. Yes, we will use water as solvent to remove let's try this one. I will draw it in the next page. So what we are doing is like we take the product from CSTR and PFR, so and then we will pass it to a flash separator. So that should separate your light components from the heavier components. In this case is ethylene dichloride. So this will be roughly 60% purity, but we can check this later using the Aspen HYSYS. And then we further purify them using a liquid extractor, using water as extractor. So and then you will get some bottom product, some top product. Normally we perform this as 15 degrees centigrade and 4 atmospheres. So this is the same temperature which industries use to using this type of setup, like a reboiler, and then they remove the light fractions, and then they take the pure products from the bottom, and then this should produce so you take the water out, and then you take the light component, which is ethylene dichloride. So at the end you will get something like this. You get two phase. So you get water, and then you have ethylene dichloride. So this water will contain some of the impurities, so this will be more pure. Normally you will get 0.92, around somewhere around more than 90% purity. Yeah, so this liquid extraction should ensure 90% purity. And then we are going to go for the distillation process to get near 100% purity. Oh, sorry, the reboiled absorber. So yeah, that's correct. We'll go for the, I don't know how to draw this one. I'm not good in drawing this. So we will connect it to your reboiled absorber. So we can decide the number of stages later, but anyway we can try from, let's put 17 stages. We can change this and then we can check in Aspen HYSYS how it affects the purity. Yeah? So it will be like a reboiled absorber. So this is something that you can play with Aspen HYSYS. Yeah, so you can add even one more liquid extraction unit instead of a reboiled absorber. Obviously it won't make any big changes. Yeah, so keep these things in the mind. And also this liquid extraction, you can perform it as one stage or you can perform it in multiple stages, so 1 to 5. So in this case we are going to stick to in 5 different stages. 5 different stages. So we are going to perform liquid extraction in like for 5 stage liquid extractions. So that's the thing you should take a note. And then after that we are going to use a reboiled absorber in order to get near to, take the bottom product from down, near to 100% purity, and the top product will contain hydrochloric acid which can be recycled. So this is the final final product that contains HCl, which is removed from the oxychlorination process. So obviously you can recycle this back and then pump it back to your CSTR unit, sorry, to your oxychlorination unit, your PFR. So how to draw this? So you have ethylene, Cl2. You're going to split ethylene into 2. So this is your CSTR, that's your PFR, and you add, for the moment we have something like a temporary stream, HCl, and then you take the product stream and then it goes to your flash separation, and then this one we take the bottom product and then we go for a liquid extraction. We take the water out and then top is your product, which should be ethylene dichloride, and then it should goes to the reboiled absorber, and then you take your 100% pure or 99% pure ethylene dichloride, and then you take the top product which should contain HCl, and then you recycle back to your plug flow reactor, and then you can delete this stream. So what we see is like a completely a closed loop. So all you see here is some product goes inside ethylene, chlorine, and then you get a hydrochloric acid which is recycled from the entire process. Yeah. So this is something we call it as a balanced process. So it's tightly closed. The material balance is tightly closed. And that's why at the moment vinyl chloride manufacturing is a very clean process, because there is practically there is no waste that which is released to the environment, yeah, because we are going to recycle back the product, the chlorinated, not chlorinated product, the hydrochloric acid, which is the byproduct, and then we are going to recycle back into the plug flow reactor. I think so far so good. I think I recorded this video continuously for more than 2 hours. I took only a short break in between. I think I need to take some rest. So what I'm going to do is like I will split this video into maybe 2 to 3, and then I will upload it. So try to watch it carefully, take a note, try to draw the flow sheet by yourself. Take all those tiny little informations, like how much goes inside, what's the temperature, pressure, reaction kinetics, and the name of the unit operations like a CSTR, PFR, and then there's something I call it as a separator, liquid extractor, and then your reboiled absorber. So if you look at here already, you see some major unit operations here, like CSTR is a major unit operation, PFR is a major unit operation, liquid extractor, that's a major unit operation, and then your reboiled absorber, that will be a major unit operation, and then obviously flash separator, that's a minor unit operation. So we are going to do all this calculations using Aspen HYSYS, but at the moment we are learning, we are covering the theoretical, not the theoretical features, just to say we are getting the record information, to design a full plant. I think this is good. So what I'm going to do is like I will upload whatever I covered so far. So probably you will have a lecture 2 in maybe part A, you will have at least I will write it here. So lecture 2 will be part A to maybe part D. So try to watch all of them. So, and then lecture 3 we will directly go to Aspen HYSYS. So this is the best way to learn this software. Last 2 years I tried different methods, and the student feedback is not really great. They really don't like if I start directly with a software, which so that's why I'm trying this way. I think this should work well, I think. So what we are going to see in the next part will be something like so we will take this ethylene dichloride, and then we will take this to the pyrolysis unit, which will be again something like a plug flow reactor. So I will use the PFR as a pyrolysis chamber, and then we will heat it to some very high temperature, where you will get your vinyl chloride monomer. Let me check the reaction stoichiometry one time. Yes, you will get, let me write it here, so C2H4Cl2. Upon pyrolysis you will get the desired product, vinyl chloride monomer plus HCl. So we will also recycle this HCl back to plug flow reactor. So and then we will add a plug flow pyrolysis chamber, and in order to produce vinyl chloride monomer, and then we will try to get we will try to purify this vinyl chloride monomer using a distillation column. So this is another major unit operation. So distillation column, so what I'm going to cover in this distillation column is something like I will tell you how to design the distillation column, and how to get the parameters like a number of trays and other things, like what should be the temperature of the reboiler, what should be the temperature of the condenser, and so on. So these are the information that you need when you are going to to design the distillation column, and or where your feed should enter, like in which stage your feed should enter. So this type of things you can calculate very easily using Aspen HYSYS. So there are few tricks to that, so I will teach you those tricks. So and then you will learn those tricks, and then we will go on to design the distillation column. So at the end of the day you will get a pure vinyl chloride monomer, and then we will try to check the how efficient our process is, whether we are nearing the stoichiometric efficiency. Say like you start with say 350 mole of ethylene, are you getting 350 kilomole per hour of ethylene goes into the process, and we will check whether are we really getting 350 kilomole per hour of vinyl chloride monomer from the process. Yeah, so we will deal with this in the next lecture. Yeah, so in the next lecture what we are going to deal is how to take this ethylene dichloride, and then how we are going to pass it to the pyrolysis chamber, what are the products that we can expect from the pyrolysis chamber, and how we are going to purify it. Yeah? And then lecture 3 is just going to be Aspen HYSYS lecture 3, lecture 4, lecture 5, and 4 and 5. So we need at least 3 lectures to cover all this topic of vinyl chloride monomer. So what we did is like we are going to do a full chemical, final year chemical engineering design project. So it's not a bad idea. At the end you will you will really like, like once you learn Aspen HYSYS, I think that will make you like nearly a full chemical engineer. So thanks for listening.